essentially in-place updates to data structures. Now they're append-only blah blah lists, but trying to do that with some immutable data structures like RDB is painful. You could imagine Databricks putting in something like that. But I don't know. I think they have other things that they're going to be more successful at doing. It's reasonable to think about taking something like Flink, which is sort of a more capable infrastructure in terms of what it can implement versus not, and think about putting that sort of thing in. So it's totally possible that the jelly stream stuff could just put some of these timestamps on their records, and that would be a thing.
Actually, that exists. They call them continuous queries.
That exists. Sorry.
For the differential queries, like SQL queries.
Yeah.
They call them continuous queries.
Excellent. So continuous queries for SQL are a big thing, but they don't involve iteration. Yeah, they don't. Right. So so they look a lot more like the traditional, I would say, stream processing style things, where diffs and new records go through a query function. Cool. Okay. Thank you very much. I'm around, so if you have questions.
Next talk will be about Rabesque, distributed graph mining platform. So be back in about 50 minutes, and
informatie kunnen opzetten. Dat is een leuk verhaal. Ik vond technische informatie, dat is wel informatie. Het eerste jaar gaat de technische informatie hetzelfde, over 1000. En toen werd de opleiding gegeven. Dus ik ben maar blijven zitten, want ik heb nog steeds
heb je eerst dat methode?
Ja. En dat ben ik geworden getoond. Ik dacht van, nou ja, eerst een paar vakken allemaal hetzelfde, dus laat ik maar blijven studeren. En ook het toetaan een technische vakken zo. En ik ga ook naar de school 3. Maar wat abstracter zit, na een paar jaar ben ik een beetje gestopt. Ik wil eigenlijk bouwen in de klas. Klussen. Zoals een studio. Wat dan? Gasten praten. Als je informatie weet, heb ik dat gedaan. Dyslexie. En dat is het van. 7. Ja, het was klaar met studie
Wacht eens, je hebt dus even de universiteitswoning, heb je technische informatie gedaan?
Nou, eigenlijk gewoon informatie. Ja, want informatie was wel een label, die werd gelukt, maar er was niks en ik heb die studio gemaakt.
Nee, dat begrijp ik. Maar
een bachelor bedrijfskunde gemaakt, wat eigenlijk gewoon geen opleiding ik heb ook in de OC-studie gezeten. Dus dit doet een beetje op wachtenstok denken. En daar hou ik van. En de zelfstandig ondernemer, die heeft altijd heel hard gewerkt. Gewoon bomen rooien, glazen wassen, garage houden. Dat is een beetje mijn referentiekader. Ik hou van Ik word heel chagrijnig van mensen die heel belangrijk doen en niets weten. Dat wordt echt,
Sorry,
ik word echt niet chagrijnig.
No, you still. Sorry, I have to see if the.
oh, sorry.
Ik vind het leuk dat een organisatie inrichten. Niet echt leuk. Voor de ruzie. Voor de tijd voor de Ja, je hebt geen idee hoe ze dat ja, dat wordt echt goed. Met heel veel. Daarvoor. Die PO's. Ja, oké. Maar dat is nog geen reden. Dat moet ik ook nog eens zeggen, want dat is gewoon een
zijn. Wat wil je nou? Ik ben geen van. In die eerste zijn goed. Ja, alleen dat moet je nog voelen. Hij is niet aan de plek. Dat zie je heel dat kan niet. Dan ga je even met feesten, maar hij is speel. Speel. Even dat kan zo doen. Dit is behoorlijk verantwoordelijkheid. Ja.
Dit is een space upgrade, so you can also find
We hebben nog gesproken. Predikte theorie.
Tijd komt er wel naar jou toe. Maar gewoon niet. Top. Leuk. Ik heb het niet gezien.
So, welcome back everyone. I hope you're not yet tired and exhausted because it continues a pretty great work when you graph that through up to the end. So I'm happy to welcome Jonas, who will present Rabesque, a distributed graph mining platform. And I'm very interested what it's about and what you can show us how you apply this graph mining platform to the So, welcome Jonas. Please find a seat to not disturb the
So, first of all, thanks for the invitation and good afternoon everyone. My name is Jonas Ganos. I'm a senior scientist in Qatar Computing Research Institute, which is based in Qatar. So I just flew from 20-something degrees to this nice weather here in Belgium, but it's pretty nice. Nice to meet you. So today we're going to talk about our system Rabesque, and we have an accompanying website rabesque.io that you can check. And what is Rabesque? Rabesque is a system for distributed graph mining, which is a little bit different than what maybe you have heard so far about distributing about graph processing. It consists of different algorithms. We have published recently Rabesque in SOSP 2015. So if you think that you cannot follow me in the presentation or you want to read a very nice paper, I think it's very well written, please go and check the PDF. And this is a joint work with colleagues from QCRI, like Carlos, who is a student, Alexander Fonseca, Marco Serafini, myself, Mohammed Zaki Nasser. So, like, about this talk, like, we have to start talking about graphs, right? And we say graphs are ubiquitous. Hopefully, in this kind of workshop, I don't have to explain why graphs are everywhere. It's even written here, graphs are here. Anywhere you have them, logos on t-shirts, etc. And you have them in social networks. You have them used them for recommendation, used them transportation. There are various fields where you can model the problems they have, ask graph problems, and try to do analytics, try to understand what's happening in these graphs. Now, as a community, we know how to scale some particular problems, like the graph computation problem. So we are talking about connected components that we were discussing before, page rank, label propagation, shortest path, etc. We know how to solve these kind of problems. And for instance, Facebook, okay, can scale processing to graphs that contains trillions of edges. And you have systems like Apache Flink, for instance, that can do multi-factorization that is used for recommendations for tens of millions of users and millions of objects, etc. So this is this is in a sense a solved project. Now, it didn't used to be the case before the Pregel paper came in 2010 that shows a way of how to distribute, how to provide abstractions in order to be able to distribute this kind of processing. And after Pregel, like, there were many systems that were introduced, like the gas, gather, apply, power graph, then you have also, and you have a lot of systems like Apache Giraffe, Flink, etc., etc., etc. Now, despite this kind of progress, there remains important problems, classical algorithms, that cannot be readily formulated using the TLV paradigm, okay? Because like Pregel is like think like a vertex. So what are these problems? The problems are the graph mining problems. So what you're trying to do in graph mining, you try to discover patterns of interest. So for instance here, what is the typical input? You have this kind of input graph, and you have vertex 1 who has a blue label connects to vertex 2 that has a yellow label, etc. And you're looking for patterns of interest in the sense that you try to find out that the blue label connects to a yellow label, connects to a red label, etc. And then you have the embeddings, which like the instantiation of these patterns are the embeddings. Now, what I want to say. So the thing is, like, you don't know the pattern. We're not trying to do pattern matching. The pattern is part of the question, okay? And you want to use it has some algorithm properties that you're trying to find out. For instance, one case is the finding fully connected subgraphs, finding clicks. So here, what we do, we try to find all the clicks that exist in this graph, which like the colored graphs here. And this is for an unlabeled graph. Other kind of problems are the motifs, network motifs. You say, I want to find all different ways that three vertices, for instance, are connected, which can be a line or can be a triangle that we have here. For size 4, we have 6 different combinations, okay? And these are the ones that we're talking about in the beginning, that they are the patterns. We want to find the frequency, how often in a graph you have this pattern happening, how often you have this one, how often this one, etc., etc., etc. Another kind of application that uses label is the frequent subgraph mining. Basically, you have a large graph, a label graph, and you say, I want to find all the subgraphs that have a frequency above some value that I put. For example, frequency above 6. So for instance, in this one, one of the patterns that you're going to find is the subgraph, this one here, that has this instance, this instance, this instance, this instance, this instance, etc. This is another example of a graph mining algorithm. Applications. There are many different applications. You try to find, you can use them for community detection, link spam detection, you can use for RDF graphs to attribute patterns, you do in biology, etc. There's a number of applications you have. Now, the main thing that I want to talk about, the graph mining problems, are the challenges. So what are the challenges? Typically, for graph processing, when you are talking about challenges, you say, okay, I have a graph that has 1 trillion edges, okay? Here, this graph can be a challenge. And why this can be a challenge? Because the problem increases exponentially. The intermediate state, the number of subsets that you have to analyze and the embedding you have to capture grows exponentially to the size of the graph. So for instance, for this tiny graph here, which basically is the cyclic graph, you start embedding size of 1, which basically corresponds to a single vertex. You have 4,000 elements. Then you grow them, because this is how graph mining works. You iteratively grow the subgraph that you can detect into your opinion. You have now 2 vertices, and you go to 22,000 instances. For 3, it's 335,000 instances. And for embedding size 6, you have 1.7 billion instances. Okay? And this is what distinguishes graph mining to graph analytics. People run graph analytics like PageRank, Connect Components, etc. The problem is that you don't care about the input of the graph. You care that the intermediate state is huge and grows exponentially. Okay? What are the other challenges? There are no standard ways to solve this kind of problems. You can think, oh, but we have the thing like a vertex, and we can apply the thing like a vertex to solve this kind of problem. But as I will say later, this is not a very good fit. There are no standard ways to distribute this kind of process. Okay? And above all, it's very complicated for programmers to sit down and implement correctly this kind of algorithms. The problems are the many isms that you have to solve. For instance, in order to be able to detect and identify repeated embeddings, you have to do automorphism. Okay? What does automorphism mean? It means that while you're doing the exploration, you can see an embedding as 1 to 3 or 3 to 1. This thing is the same embedding, so you cannot take it twice. You have to discard one of them and keep only one. And the other problem is that you have embeddings, you have the 3 to 1. You want to know what is the isomorphic pattern that you can use in order to aggregate. And this is a very expensive operation. And to summarize, in a sense, you have something that grows exponentially, the intermediate stays exponentially, and you can have computation that's really expensive per embedding that you require. And above all, we have to say here that not all problems are tractable. Okay, your cluster cannot grow exponentially. You have to be realistic on the parameters you set for this kind of algorithms. Now, let's say you want to implement this and run one of these algorithms to your system. What you're going to do? So you can start with getting either a code that exists out there and try to run it, or you get a PhD student, log in the room and say, look, go, and start programming this. Okay? So you have to do everything by yourself. You have to do the automorphism, isomorphism, etc. And you can have a very efficient implementation because you try to solve the problem at hand. But of course, like typically they don't think in for transparent distribution. It's like all these kind of algorithms that you find in the literature, most of them are for single thread. Okay. Now you can say when we started this kind of project, we thought like, can we take these algorithms that already exist and make them distributed? And in a sense, because these algorithms work on a pattern level, it's a thing like a pattern, in a sense, kind of approach. And you can read more details about this in our paper. Now, if you try to do this, the problem is that you have extremely high hotspots. Because in the case of motifs for size 4, for instance, you have only 6 patterns that you try to aggregate. That means no matter how many threads your cluster has, you can only use 6 threads for computation. There is nothing more you can do there, unless you start really thinking of how to split the load, etc., which is basically what we're doing. Now, since in this case the distribution is the problem, an obvious way, and probably the way that most practitioners will take is, okay, let's use the thing like a vertex. There are so many systems out there, I'll take one and start using it. Now, again, it's not easy to program. You have to deal with all these kind of automorphisms yourself. You get the distributed nature of this kind of system, but the problem is that it's really, really bad choice to use because it's really sucks, let's say, in performance. Why it sucks? It can be 2 orders of magnitude slower compared to the TLP approach. The reason is that you have to replicate the embeddings constantly in order to send it to vertices that know how to expand it. And to give you an example, when we run for a small graph one of our algorithms, it requires 120 million messages to be exchanged. And our approach takes only 130,000. So this makes it like 2 orders of magnitude more slower compared to the systems that exist out there. And we have the question, okay, you have scalability, but at what cost? So of course, what is the answer? Is Rabesque, as you can guess. We propose a new execution model and an accompanying system to be able to solve this kind of problem. And in a sense, we say, we want to think like an embedding. This is the unit that we are going to work. And the programmer, this is the unit that has to think in order to code an algorithm. It's purpose-built for distributed graph mining. The current system works over And the important thing is that it's like we focus on simplicity. We wanted to make it easy to be able to develop this kind of algorithms. Okay. Of course, as you can guess, we get getting like successes on all these kind of dimensions since we pick the dimension. So let's go back to concept because before I show you how code looks like. This is the input graph. Okay, this is some pattern that we'll be looking for, and these are the embeddings. So for instance, for the blue, yellow, red, an instantiation is 1, 2, 6, or 1, 3, 6, or 4, 2, 6, etc. Okay? Now, if you want to program for clicks, what is the actual code that you're going to use? This is the code. If you want to compute clicks, okay? It's a little bit cleaned up. I removed override, etc. The embedding is not really an embedding, it's vertex induced defense of exploration, etc. But it's something that you can do in very few lines of code. So, what is this programming API? It's basically a process filter. So you say, what is the filter? Filter takes an embedding. It says, it will decide, does it match my criteria or not? If it matches my criteria, I continue to the process, and I process it. If it doesn't match my criteria, I just discard it. So, as a programmer, as a practitioner, you don't have to care how I do the exploration, if it's automorphic or not, if it's what is the isomorphic, etc. You don't care about this kind of things. These things are handled by the system. Okay? I'm not going to discuss about these last two. I will come back later on. I will explain to you, but it's something very simple. This is basically incremental, checking if this is a click, and this is just an optimization to stop the exploration faster and more easy. If you compare this to the state of the art, which actually Frank Marcel pointed to us that it's not the state of the art, it's Maze. It has 4,006 lines, 21 lines of code in order to do it. It's written in C. What about motif counting? In motif counting, we want to be able to find all the different embeddings, like any kind of combination of connections. So basically, we don't filter anything. So filter just returns through here. And the process, what it just does aggregation, it just maps. Like I have removed here the instantiation of the init function. Okay, this is just an aggregator and says, get the embedding for this pattern, and then we have defined that it's just doing an incremental thing. And this is the code for motifs. Again, state of the art, 3,000 lines of code, dry scan. For FSM, it's a little bit more tricky, the code. And most of the tricky part is like how you count the frequency, because I just say, yes?
Just a quick clarification. What embedding is a subset of the edges from the original graph.
Embedding is an instantiation. So like the pattern can be blue connects to yellow, connects to red. And the instantiation is that the vertex 1, which is blue, connects to vertex 2, that it's yellow, connects to vertex 6, that it's red. Okay. So like most of this code is like how you compute the frequency, which is not as easy as when I explained the example, because you need to have some properties called adimonchronicity, etc. But we don't, like, we can forget this now. But basically, it's like 212 lines of code is just to compute the frequency, etc. The baseline gram is more than 4,000 lines of that code. Now, of course, you can say, look, you gave us something that's very easy for the programmer to use. It's sort of like trivial to think. But what will be the performance? Probably the performance will suck with all this abstraction we used, etc. And what we did here is like, we tried to measure Rabesque using a single thread versus the centralized baseline implementation that exists out there. So basically, we compared Rabesque, which is written in Java, with motifs and clicks, which like this implementation are C, and the FSM is in Java. What we see is that actually Rabesque sometimes can be faster than the centralized, for example, for motifs. And for clicks, it used to be much worse, not much worse, a little bit worse, but now with some optimization we have done, that's in the system, it's actually much faster than what the C code does. And for FSM, it's, let's say, almost the same. What is the important thing though? That the system is scalable. So something that will take you 2 hours, 24 minutes to run in a centralized single-thread environment, we can run it in 25 seconds when we use 650 cores. Okay? Or something that can take more than a day to run, it can run in 1 minute and 28 seconds. It's like a huge reduction. So it's not only that it's only scalable, but it's also efficient. I will explain later why this is the case. And we have to say here that for frequent subgraph mining, this was the first distributed implementation. So there was no algorithm that will take the base centralized algorithm and make it distributed. How we can achieve this? We have some very elegant sort of optimizations. We can avoid redundant work without any coordination between all the workers that in the cluster they work in order to produce the output. We have very high subgraph compression because remember the problem with graph mining is the explosion in the intermediate state. That's why we think like a pattern, the typical approaches work on a pattern level actually, because they don't want to instantiate all the beddings, they generate them on the fly. We need them in order to be able to distribute the load and avoid having hotspots. But we need to have them as compact as possible. So we have introduced the over-approximate direct translated graphs in order to do this. And we have an efficient aggregation based on the two-level pattern aggregation. So basically, what is this? Is you have an embedding, and you want to know to what pattern it corresponds in order to be able to do the counting, etc. This is a very expensive operation because it involves the isomorphism. And we managed to solve this in a very nice way, very fast. So I'll explain later. So the outline, okay, this is just like the fundamentals. So in the beginning, when I said about graph mining how it works, I said that you try to grow the pattern and the embeddings in an iterative way. Okay, so you go from subgraphs of size n to subgraphs of size n plus 1. So how you do? You start. This is the input graph 1, 2, 3, 4. So you start with depth 1, all the vertices, then you expand them. You connect. Basically, you take all the edges that they connect to and you replicate them. Okay. So this is for depth 2, all the embeddings that you have. Depth 3, you have all this kind of connection, all these embeddings. Now, Rabesque, I already said, but to make it more crystal clear, splits the responsibilities, like what the system does and what the user does. So the user responsibility is to sort of apply the filter and the process, and some other things that are high, but these are the most important things. The Rabesque responsibility is to do the graph exploration, the aggregation, which is called the isomorphism, the automorphism detection to avoid duplicate work, and do the load balancing. So why the system is so efficient? Because this part of the code that we have here takes 0 amount of CPU time compared to this amount of code. We never export these things. You can actually override them and implement yourself, but we have done this as efficient as in the centralized implementation, and we even did some tricks that not even the centralized implementation was cut. That's why we can beat them for some time. So you don't need to care about these things. Only about these things. Now, how does the thing like an robotic model work? So you start your exploration step 1. Let's say you go to exploration step 2, that you have as an input the embeddings on step 2. You pass them here. You find what are the candidates for extension. Basically, you follow the graph and say, okay, 2 connects to 3 and 6, so this will be candidates for extension. Then you pass them to the filter, okay, and say, okay, first of all, here you do the automorphic check, because if you had the case that it's 6 to 1, the reverse, you're not going to prune, you're going to prune, you're not going to process at all. Then you pass to the filter. If it doesn't pass, if it's not an embedding that you care of, you simply discard it, because there cannot be any subsequent embeddings that will have the properties that you want, if the basic one doesn't have, the base one doesn't have it. If it returns true, because it's the one you want, then you process it. You do whatever you want to do. Either you aggregate, you save it, or you do something else. And then you have this kind of process, like if you should expand or not. Why we're having this? Because if you are interested for depth 5, if you do the pruning on filter, then you just go one more step, that you just reject everything. So we can put this like this in an optimization. And then it passes to the output, and then the output, the next step becomes the input, and so forth. And so Now, again, let's go to the click finding example. Now I can explain you a little bit more what is this click. So what this clicks does is like, you can check if it's fully connected, or remember that we're doing everything incremental. So if you're at depth 4 and you try to check to see if an embedding represents a click or not, you know that at depth 3, it's already a click. So then you just want to find out that the new thing that I added, how many edges it had to the previous vertices that existed there. So if the number of edges you added is equal to the number of vertices minus 1, that means that it will be by default. We also guarantee completeness. What this means is like, there cannot be the case that you filter something here as false, but then later on embedding will be true. This is not the case. And for this, there is a requirement for this that's called anti-monotonicity. And this is, for instance, why for frequent subgraph mining, the counting, it's not as easy as say, oh, we have 6 embeddings. It's a little bit more complicated to do the counting for, in order to have this kind of anti-monotonicity. Now, it's not that all kind of algorithms will focus on a single embedding in order to decide what they want to do. For instance, for FSM, you only care about the frequent kind of pattern. So you need to be able to prune, okay? So you need to be able to do some aggregation in order to do counting or do pruning, etc. Now the aggregation happens in parallel with the exploration step, okay? And embeddings are written as soon as aggregated values are ready, which happens on the next super step, basically. So how does it look like? It's like after you get the initial embeddings, you have an aggregated filter and an aggregated process. And then you can decide if you want to throw out what you already have, if this is not, for instance, a frequent one or not. And this happens before the process and filters kick in. Now, the full sort of like full Rabesque API is the one I described here. It's like you have Boolean filter, just returns true or false. You're doing the process, okay? The should expand, which basically terminates early if you pass some maximum depth. The aggregation filter and aggregation filter based either on embedding on pattern in order to do the pruning. The aggregation process if you want to do something based on the, like if it passes the filter. And handle no expansion, because in some cases you say, okay, there's nothing to do. Maybe you want to be able to do something in the case you have no expansion. We have some performance improvements API here in the current API. So basically, the second one basically does canonicality checks. Okay, so you can override the canonicality check that we're doing. Basically, it can override the automorphism check that we're doing. And the top one gets the list of possible extensions, and it can work on this. For instance, you might decide that you want to do a special form of motifs that has some extra requirements, multiple colors, like I want only motifs that have 2 colors, etc. So instead of getting all the extensions, you can play with this here and you can change. You can have the performance improvement. And you have the function provided by Rabesque. It's basically the output. You just output the embedding. You have a map, which like this is very similar to the map in the rate aggregation. So the system is implemented on top of Giraffe. I will say this later on. But even though we don't use the thing like a vertex, so this kind of functions are really following the way that Giraffe describes aggregation. So system architecture and optimization. So we have implemented the system on top of Apache Giraffe. We don't really use the thing like a vertex, and basically like the mechanism that Giraffe provides. We just use like the underlying mechanism of computation and messaging, etc. And we just picked Giraffe simply because we knew it. We knew the source code and we knew how to make it work in ways that we wanted to make it work. Right now we have a team working on a Spark implementation. It can be on any other system that supports the bulk synchronous parallel model, because this is what we require. So what is in a very high level happening? You have a number, you have the embeddings as an input that like these embeddings go to this worker, this embedding go to this worker, etc. The worker produce other embeddings that they are shuffled across the server and so on and so forth. Okay? Now, how you're going to kind of work? So assume that worker 1 had the bedding 1, 2, and worker 2 had the bedding 3, 2. And both of them, they decide to expand it. So worker 1 expands 2 and added 3, and then you have this kind of a bedding. Worker 2 expanded 2 but from the side of 1, and then have this kind of a bedding here. Now you have a problem, because you have two workers working on basically the same bedding. And you need to be able to prune this out. You should not, like only one of them should proceed and actually process this embedding. Now, you can do this with synchronization coordination, but remember we're talking about billions or trillions of embeddings, so this cannot work. So the way we do it is we're using the automorphic thing. We call it this canonical. So we define the way that this is a canonical way. For instance, they have to be sorted by, it's not as simple as this, but let's say for instance, it's sorted by the vertex say 1, 2, 3. So this is canonical, it turns true. This is not canonical, so it will be rejected. And the code, the complexity of doing this is linear. Okay, so we can avoid doing all the coordinations. It's very, very efficient. The other one is about how we're doing aggregation. So you have these embeddings, 1, 2, 2, 4, and 3, 5. Which basically capture the pattern blue and yellow. Okay, so this is the canonical pattern. This is the one we want to find out. Now, if we are doing this on all the embeddings, we have to do 3 times. Oops. So we have to do 3 expensive operations, okay? Instead of doing this, what we're doing something called quick patterns. We just do a linear scan, and we create patterns. So in this case, would be blue, yellow, yellow, blue. We do the counting on this one, and then we do the expensive operation, using the isomorphism check in order to find the canonical pattern. Now, from three expensive operations, we went to 3 linear matching to 2 expensive operations. So this here in this example might not seem a lot, but in reality this might be 1 billion operations, and this would be like instead of doing 1 billion expensive operations, you end up doing 6 expensive operations. Okay, so basically the whole problem of isomorphism that we have to solve for this, it's basically disappeared. We don't care about this problem. And also I have to say here that you don't always, not all graph mining kind of systems have this kind of problem. These problems come when you work from embedding to pattern, okay? If you are working from pattern to embedding, you don't have this because you already know the pattern you are in. And the last one is like how to handle the exponential growth, okay? How you can handle trillions plus of different kind of embedding. You can use things like compression or prefix trees in order to compress them, but this still is not enough. We have to do something to even decrease more the amount of memory we're using. And for this, we introduce the over approximating tags, which basically compress the embeddings into less restrictive superset. Okay, what does this mean? This means that when you are reading from this data structure, you're going to read embeddings that don't exist in the initial input. And you have to do something in order to be able to remove them. Now, luckily, we have a lot of tests. The test number 1 is to check if it's canonical or not, because you know if it's not canonical, it will never be in the input. And then you can also test the filter. You can use the filter functions of the user. If it doesn't pass the filter function, that means that it shouldn't be there in the first case. So for instance, here you see like you only encode 1 level of connections, okay? Like that 1 connects to 4, and that's it. There's 1 here connected to 4. And then here if you go from 3, 4, you see 3, 4, 5. It's the only one that existed, and not 3, 4, 2. But we can prune this. Another question will become, is it really worth it? Because you sort of like exchange memory for more CPU. We're going to show you that it really makes a difference. Some performance numbers. We did the evaluation using 20 servers with 32 threads each, 10 gigabits networks, and we use, of course, the 3 algorithms. And we use different kind of graphs.